In this video, you're going to learn more about Boolean algebra. Hopefully you'll be familiar with the dot notation, which would be used in AS computer science. And here we're going to expand on that and look at some of the identities and laws that you'll need at A2. So as I said, this video uses dot notation for Boolean algebra. And if we look at an example logic gate or logic circuit, we can write the yellow circuit out as A dot B plus the negation of C. And remember, the dot means it's A and B. The plus means it's an OR. And that negated C means it is not C. So for identity, if we use the A symbol, A and 1 will give us an output of whatever A is, and A or 0 will give us an output of whatever A is. So just quickly to explain how this works, if you think of it as a logic gate, and the first input is A and the second input is 1. If A is 1, then 1 and 1 will output 1. If A is 0, 0 and 1 will output 0. So the result is whatever A is. And for the second one, for the OR column, we draw this logic gate. We've got A and 0 as inputs into the OR gate, and so if it's 0 and 0, the output is 0. If it's 1 and 0, because it's an OR gate, the output is 1. So again, for that gate, the output is whatever A is set to, and that's the identity. For null, it doesn't matter what A is, because in either case, if it's A and O, the output has to be 0. So it doesn't matter what A is. And for A or 1, it doesn't matter what A is, because the output will always be 1. With idempotent, that word means that it's an element of a set which doesn't change in value when you multiply it or otherwise operate on it by itself. So A and A is still A, and A or A is always A as well. So with inverse, you're applying negation to your input, one of your inputs. So if we have A and not A, then you're always going to get 0. And if you apply A or not A, you're always going to get 1, because one of the values is going to be 0 and one of the values is going to be 1. So with commutative, changing the order of the operands doesn't actually change the result. So in this example, if you do A and B, that's exactly the same as B and A. Same with the OR. A or B is exactly the same as B or A. So, and with associative, it's just like normal arithmetic. It's the order we apply the operations when there's 2 or more of the same operator are involved, doesn't matter. So if we have A and B, and the result of that is ANDed with C, it's exactly the same as A and C, and the result ANDed with B. With the OR, associative is the same, so A and A or B, or C is the same as C or B or A. With distributive, it's different from normal maths because if we have, this is where we combine things, A or B and C, we expand that out to be A or B and A or C. And another example is A and B or C, which is equal to A and B or A and C. Absorption needs a little bit of explanation. So this allows us to simplify a Boolean algebra expression. So we have A or A and B. Okay, I'll quickly draw this out. We can follow this through and say that if A is 1, then the output's got to be 1 because it's an OR. And if A is 1 and B is 1, well, the output's definitely going to be 1 because A is essential for the OR gate there. If we say that A is 0 and B is 1, A is 0 gives us a 0 for the top of the OR gate, and a 0 going into an AND gate outputs a 0. So it's 0 and 0, and so we can simplify this expression by saying that A or A and B is just A. We'll do the same for the second expression, which will be A and A or B. We draw out. If A is 1, that's good. Feeds into the OR gate. Because A is 1, that automatically outputs a 1, which makes the output 1. If A is 0, then the output is going to be 0. If B is 1, then it depends entirely on what A has. So the output, or simplification in this case, is simply that A and A or B is A.